It's Mrs. Niederhauser. Welcome to class today. All right, 2 more, then we're done with Unit 1. Okay, today we're going to be talking about Unit 1, Lesson 12, which is kind of just not necessarily a repeat, but an extension of 1.11, which we did last time. Today we're going to be talking about this idea of real and complex, which we've technically already introduced, but we're going to continue talking about it. So if you haven't already, pull out a piece of paper, pen or pencil, Word doc, whatever you need to take notes, okay? And we'll get started. All right, so like I said, Unit 1, Lesson 12, Real and Complex Numbers. So I think what's important is to reiterate what we talked about last time, which was we introduced imaginary numbers. Imaginary numbers come from, again, remember I asked you to memorize 2 things. It comes from this idea of square rooting a negative number. Okay, I is defined as the square root of -1. Before last time's lesson, we had never seen a negative underneath a square root. And if we had, we would normally just say no real solution. Okay, normally, originally, that's what we would say. If we were ever given the square root of a negative number, we would normally say no real solution. And that's true because it is no real solution. It's an imaginary solution. Okay, so with that being said, I want you to notice something though. And this is what we're introducing today or talking about more deeply. Okay, we introduced this concept of imaginary numbers. Okay, where we introduce the fact of I. Okay, where it comes from, what it is. Okay, a pure imaginary number, again, we talk about being just the imaginary number itself, and that's oftentimes what we dealt with when we were talking about our lesson last time. But now what we're going to introduce more fully is this idea of complex numbers. Complex numbers is a combination, okay? It's a combination of our imaginary numbers, okay, and our real numbers together. Okay, so A being real and B technically being our real number, but in this case, what makes it imaginary is now that it's times by I. Okay, so B times I is the imaginary part. So real plus imaginary creates this idea of complex. Couple reminders. What do we do now? When do we use imaginary numbers? How do we use them? What are we going to do to use them? Okay. The one thing that I wanted to you to notice first, and probably foremost, is these 2 things. These are the things that I want you to be memorizing. These are the things that need to be drilled into your brain. And that's why you're going to see them a lot in the next couple of slides. We're going to talk about them lots. Remember, the first and foremost, I equals the square root of -1. That's the definition. That's what it is. Okay, again, we talked about it in the fact that mathematicians, what's next? Okay, we had square roots and we simplified square roots. Well, what if I throw in a negative underneath a square root? Well, that's where this imaginary number comes from. Creates this imaginary number. But what if I took I, which I know is the square root of -1, and I squared it? Well, if I square it here, I've got to square it here because they're equal to each other. And we know that a square root, or we should know by now, that a square root and a squared cancel. That's what creates this idea of I squared equals -1. Okay? Again, because of that operation, that they're opposites, leaving us left with just -1. You could also think of it like this. I squared is the same thing as saying I times I. Well, I is the square root of -1, and I is the square root of -1. Well, remember, what we're going to do is we're going to multiply our square roots together. So now I have the square root of -1 times -1. The point of this is to have pairs, right? Oh, look at that. I've got a pair underneath my square root. I pull that number out. I don't have anything left inside. That number ends up being -1. So there's multiple ways of thinking about it, okay? I could give you an example. We could do a square root of -56, okay? As a reminder, when simplifying a negative underneath a square root, the first step should be to separate that negative from the positive. So negative 1 times 56 is the same thing as negative 56. But one thing that I'm going to do is I'm going to separate out that square root of negative 1 because I know that the square root of negative 1 is actually something else. And that something else being I. And then from there, I can simplify down the positive square root that I now have. So I could take I, and then instead of writing 56, I could think of numbers that multiply to make 56. One thing that I'm noticing with a lot of people is they're still having a hard time with figuring out two numbers. Here's how I do it. I pull up my calculator. My number is 56. I'm going to take the number 56 and just start dividing numbers. The first number I'm going to divide by is probably the one that's usually the most common. If I'm not dividing by 1, I'm going to divide by 2. So I get 2 and 28. That's the two numbers that I'm putting underneath my square root. And then I continue to break down the numbers that can be broken down further, which in this case would be 28. I still leave the 2. Again, I take 28, I divide it by 2 again. Sure, why not? I'll just go for it. 28 breaks up into 2 and 14. Keep going. 2 times 2 stays, but 14 breaks down further into 2 times 7. Again, goal here is you're looking for pairs. I find a pair, I pull it out with my imaginary number. So I end up getting 2 times I, and then times by the square root of 2 times 7, which is 14. Okay, so really, if you think about it as far as the differences, what makes this different? This first part, the rest of it's all the same. So this is the part that's making it different. The other part is really just the same. You just got to get the I taken care of from the beginning, or the negative for that matter. All right, so like we talked about this concept earlier, real numbers. We've talked about real numbers. We introduced it in 1.10. Okay, real numbers are defined as the following. We have rational, we have irrational. Rational numbers can be further defined as integers, whole numbers, natural numbers. Okay, remember, natural numbers are like our counting numbers. You never start with 0, right? You would always say 1, 2, 3, ready or not, here I come. Okay, your whole numbers are going to step up just a little bit more. They're going to give you just a tiny bit more. Now we're going to include 0. 0, 1, 2, 3, so on and so forth. Again, still positive whole numbers, but including 0. But then when we jump into integers, that's where it brings on the negatives. Okay, negative numbers and 0. So negative 2, negative 1, 0, 1, 2, so on and so forth. Okay. Now, as far as understanding rational numbers, okay, all of these numbers underneath or in this circle are considered to be rational numbers. So if I say the number 1, the number 1 is not only a natural number, it's a whole number, it's an integer, but it's also a rational number. But rational numbers are basically defined as numbers that can be written in ratio form. So numbers that can be written in fraction or ratio form. Now, that could be decimals. That can be whole numbers. That can be natural numbers. Examples that we've used in the past. You could have 0.1. You could have 2/3. You could have 0.65 repeating. Okay, those are all examples of rational numbers. The number 17 is technically a rational number. As far as irrational numbers are kind of like the opposite of rational numbers. They're numbers that cannot be written in fraction or ratio form. Some examples of that would be, a lot of people use the number pi, okay? Or you could say something like 2.1357234 just some decimal that makes no sense, right? Just random and weird. That's what irrational numbers are, is they're just crazy weird numbers that don't really have much of a definition to them, don't have an ending point. All right. With that being said, just reiterating what we talked about. Natural numbers can be graphed. Okay, examples of natural numbers. I'm going to change these so you can see these. Natural numbers, remember, are 1 on. Okay, again, you don't include 0. They're whole numbers. They're not fractions. Whole numbers, you're now including 0. Integers, you're now including negatives. Rationals, you're including numbers like 3.5. Again, rational numbers are our decimals, our fractions, but also still our whole, negative, and positive numbers. Okay, irrational numbers cannot be graphed, and that's what's pretty important about this. Here we can roughly estimate it, but as far as these, as we write them, okay, these are examples of irrational numbers, and they can and they can't be graphed, I guess we can say. I mean, we can graph them, but that's an estimate. That's not exact. So for us, irrational numbers really shouldn't be graphed. I mean, can we estimate where they're at? Sure. But that's kind of the difference between rational numbers versus irrational numbers. So now we talk about complex numbers. Remember, complex numbers are a combination of real numbers and imaginary numbers. Okay, take a second and I want to see if you can come up with examples. See if you can come up with some examples up on the board. I'm going to pause it. I'm going to give you a second. Try to come up with a combination. Again, maybe something that sticks out in your mind is this: A plus BI, where A is your real number and BI is your imaginary number. Take a second, see if you can come up with some. All right, here are some examples that we have. Okay, again, A plus BI is what makes up this idea of a complex number. Okay, another thing I want to make mention of is this concept is what we call standard form. Okay, A plus BI is a standard form for complex numbers. We always like to put our real part first, imaginary part last. Okay, so an example: 1 plus I, real, imaginary. 39 plus 3i, real, imaginary. 0.8, oh, that's kind of scary because it's a decimal. It's okay, it doesn't matter, it's still real. Minus 2.2i. Again, still magic, got that I on there. Okay, this part even overwhelms a little bit some people. Negative 2 plus pi I. They're thinking to themselves, no, that doesn't work. The I being attached to it forms the imaginary number. Even if it's an irrational number, it still makes it imaginary. Okay? All right. So one last reminder. Is it complicated? Well, complex does not mean complicated. It means two types of numbers, real and imaginary, together form a complex. It's just like a building complex. Buildings join together. So kind of use this as a guide, an understanding. Think of a building complex. A building complex, buildings join together. So like if I'm in a building complex, you're in this side of the complex, I'm in this side of the complex. Okay? Well, are you on the real side of the complex or are you on the imaginary side of the complex, right? That seems silly, but it's kind of a funny way to think about it. Real joined with complex, or imaginary in this case. Excuse me, I really should have said that more accurately. Real joined with imaginary creates complex. All right, let's get in some practice. Okay, we kind of did this last time, but let's continue on. As a reminder, when adding and subtracting imaginary numbers, it's no different than variables. It really isn't. I can look at these and say, all right, I'm going to circle all of my like terms. I's or X's, it doesn't matter. They are like terms, therefore I can combine them. Adding and subtracting is just like variables when you're dealing with I's. So I've got 2i minus 3i. Well, 2i minus 3i is negative 1i. And then I'm going to take negative 1i and subtract it from negative 4i. Or I guess I should say minus positive 4i, however you want to look at it. Negative 1i minus 4i ends up giving me negative 5i. Now, I don't have anything to go with my 2, so that becomes my real part. Real plus imaginary creates my complex number. So 2 minus 5i. You guys, even if it's kind of confusing at this point in time, just change the problem and think about it a little differently. Ask yourself, can you do this problem? Because if you can do this problem that I've come up with here, technically you should be able to do this problem. It's just a letter difference. Yes, does the letter mean something here, whereas here it does not? Yeah, but again, it's still the simplifying part that I want you to understand is it's the same concept. Okay, let's try another one. Okay, this is 8i plus 1i. And I'm going to change here. Negative 1 is like terms with negative 3. So I'm highlighting, underlining, boxing my like terms. 8i plus 1i is 9i. Again, oftentimes people want to automatically just do the i's first because that's our habit, like we're so used to doing that. And then the numbers, negative 1 minus 3 ends up giving us negative 4. But remember, when dealing with complex numbers, the real part always comes first. So you should really write it as negative 4 plus 9i. Keep the sign with the number. So be careful on that. Okay, I want you to try the last one on your own. Let's see if you get it. Pause it. Take a second. Try it on your own. Give yourself the practice. All right, how did you do? Did you notice that the negative 1i plus 1i, they cancel? And then really all you're left with is the 6i and then 2. Don't forget, you've got to have your real plus your imaginary. All right, let's keep practicing. I'm hoping that what happens in this part of the practice is you're reminded of something that is super, super important that we've talked about already with this lesson, but also with last lesson, okay? Remember, you've got to remember this concept that I squared equals negative 1. You should never, and I'm going to write this out, you should never have I squared left on your simplified answer to a problem. It's super important, and there's a reason why. Because, again, what we've talked about here, the I squared has a number attached to it. So you can't leave something simplified without fully simplifying it. So just like we talked about before, it's just like x's. If I had 2x times negative 3x, I'd multiply the two numbers together, which gives me negative 6. But if it were x's, I would just multiply it like normal, like x times x, which is x squared. Well, same thing with the i's. I'm just multiplying the i's together. I times I is I squared. If these were x's, I would be done. But you've got to remember the concept that I squared is an actual number. So I am going to replace I squared with what it truly is, which is negative 1. Negative 6 times negative 1 ends up giving me positive 6. Okay, let's try the next one. Remember, this is 8i times negative 1i. 8 times negative 1 is negative 8. I times I is I squared. Negative 8 times what really I squared is, which is negative 1. Negative 8 times negative 1, a negative times a negative is a positive. Okay, be careful. I will oftentimes see that people will change this into like a negative 8 minus 1, but they're timesing. They're always timesing here, so be very, very careful. Okay, I want you to try the last two and we'll see how you do. Pause it. Please, please, please try. Don't just watch me. Be like, oh, she's going to walk away for 2 seconds, then all of a sudden all the answers are going to come up. I'm not going to waste my time. No, I want you to pause it. All right, how do we do? One thing that I would say is probably something you've got to be really careful about. Negative I times I, right? Negative 1 times 1 is negative 1. This negative is different than this negative. I squared is negative 1. So see how I've left this negative still on the outside? Negative times negative as a positive. These ones here, this one's nice because 6 times negative 2 is negative 12 and just an I. It's not an I squared, so do not change it. Okay, all right, let's keep trying some. Now, these are going to be a little different. You're going to have some that we've talked about before. We're going to have some that we haven't talked about at all. But let's kind of talk about it. So these two here, we talked about a couple lessons ago. Rule when dealing with radicals. You are not allowed to have a radical in the bottom of a fraction. So remember, in order to get rid of that radical, what you're going to do is you're going to times the top and the bottom by that exact same radical. I'm going to times the top and the bottom of this by the square root of 2. Here's what happens. Square root of 2 times square root of 2 is kind of exactly that. It's the square root of 2 times 2. Because remember the numbers, because they are the same type of square root, you times them together and you can place it underneath the same square root together. Well, notice that you have two of the same number, which means it creates this idea of a perfect square. You pull that number out, you're left with 2 and nothing more. So I'm going to have 3 times the square root of 2 on top with just 2 on the bottom. I'm hoping over time you're seeing more and more of what's going on. For example, I already know that I'm going to times the top and the bottom of this one by the square root of 7. Again, why did I pick the square root of 7? Well, because the square root of 7 is what's in the denominator. So square root of 7 times square root of 7 really is the same thing as saying the square root of 7 times 7. There's your pair. Pull it out. All you're left with is 7. So I'm going to have 14 times the square root of 7 divided by 7. Here's where you got to be careful. Kind of like we talked about with imaginary numbers, the same goes for radicals. The number in front of the radical is the same type of number as the number in the denominator. They both can be divided by 7. 14 divided by 7 is 2, making your answer 2 times the square root of 7. So simplify where possible. The other one, 3 and 2, can't be simplified, so that's why we didn't simplify here. So box that so you know that one's done. Okay, now let's go over to imaginary numbers, dividing imaginary numbers. Okay, a lot of this is very similar to what we did here in the second half of this problem. We can divide these. We can divide 32 by 8. 32 divided by 8 is simply just 4, and then tack on the I. Not much more to that problem. Again, it's just like if I were to say 32x divided by 8, divide the numbers, tack on the x. Now this is going to be kind of interesting. Now this comes back to a property you learned in Math 1. Focus on the numbers first. It says 8 times I raised to the 9th and divided by 4 times I raised to the 2nd. There's actually multiple ways you could go about this, but I'm thinking that there's one way that's going to be a little bit easier than the other. Let's first focus on the numbers. Okay, 8 divided by 4 is 2, but think about what that is. I'm dividing these two, and what should be left over should be on the top because I'm dividing each of them by 4. So now I currently have 2 I raised to the 9th divided by I raised to the 2nd. Well, if you remember, when dividing even variables with powers, okay, if I have I raised to the 9th divided by I raised to the 2nd, because these both have the same base, we can subtract their exponents. Just like if I had I raised to the 9th times I raised to the 2nd, I add their exponents. Multiplication goes with addition, division goes with subtraction. So what happens is it's kind of like I'm bringing that 2 up and subtracting it from it. So now I'm going to have 2I raised to the 7th. Again, subtracting the bottom from the top. Now, some of you would maybe argue this and say, okay, I'm done, right? Like I shouldn't have to go any further. Yeah, we learned about something. If you have anything greater than I raised to the 1st, you're not simplified. I raised to the 7th can be simplified. Remember, what we're going to do is we're going to transform this into I raised to the second because we know I raised to the second is defined as -1. So I'm going to write 2, and instead of writing I raised to the 7th, I'm writing I raised to the second, and then the number that I place here is going to be how many times 2 goes evenly into 7, which in this case would be 3. 2 times 3 is 6. That doesn't make 7, so I have to tack on one more I to make a total of 7. So we know that I squared is really -1. So that's why I used I squared. So then I can deal with something that's a little bit more bearable than an I. So -1 raised to the third power. That's like saying -1 times -1 times -1, which ends up giving you -1 times by I. 2 times -1 is -2 times by I is -2. So that one, honestly, I would say is one that is definitely harder. That is an upper level question, but that is good because it contributes. There's so many different things you're learning and talking about within that one problem. You're talking about exponents, you're talking about imaginary numbers, you're talking about real numbers. You're just taking all of it and putting it into practice. Everything that or parts of math that you've learned in the last 2 years. All right, now let's finish with simplifying radicals. Okay, as a reminder, number 1, it says simplify the following. You have the square root of -45. Okay, first thing on all these problems I'm going to do is I'm going to change it so I'm not dealing with a negative. I know something about negatives underneath square roots is that -1, I'm going to fix this a little bit. The square root of -1 is I. So I can separate these. I'm kind of almost working with my properties backwards. I can separate these into my negative and my positive. Thus, when I multiply them together, it makes my -45. But because I know that the square root of -1 is I, all I have to do is separate those, create the I, and then simplify down my 45. Again, what I can do is I can figure out two numbers that multiply to make 45, 9 times 5. Keep going until you find a pair or multiple pairs. 9 breaks up into 3 times 3. Don't forget the 5 that you had on there before. You find your pair, you pull it out. Again, it goes with your I, so you have 3 times I times the square root of 5. Sometimes you will see, and I do want to make mention of this, sometimes you'll see on certain textbooks and assignments, and just depends, websites, to stick with that same idea of standard form, they'll put the I at the end, but where you have to be careful with that is that you don't want it to look like the I is underneath the square root because it's not. So that's why I think it's better just to write the I next to the 3 in front of the square root because then there's no confusion. Okay, I want you guys to try number 2 and number 3. Try those and then just take a second, pause it, and then we'll do number 4 together. All right, take a second, check them. These ones are a little more tough because if you're like me, you thought to yourself, oh, 89's got to break down into 2 numbers. Like there's got to be 2 numbers that multiply to 8, make 89. Not 2 whole numbers. So therefore, this one is as far as you can go. 89 is a prime number. So all you needed to do is take out the I, or in other words, get rid of the negative, create the I, and then you're left with square root of 89. Okay, same with this one. There wasn't a whole lot to it. You ended up breaking down 564 into 12 and 47. Found one pair of 2's, pulled that out with my I, then multiplied what was left here. So 141 was what was left. Okay, try this one. This one involves exponents with variables, so you got to be careful. So just like before, I'm going to pull out my -1, times it by the square root of 100 x to the 5th, y to the 4th. Okay, well, if I break that up, what I'm going to do is I'm going to have I on the outside, and then 100 breaks up into 10 times 10. X breaks up into 1, 2, 3, 4, 5x's, and 4y's. So I said x breaks up into 2, but I meant x raised to the 5th breaks up into 5x's. Find your pairs. Pair of 10s, pair of x's, another pair of x's, pair of y's, another pair of y's. So you got a lot of things that are coming out, so be careful. Make sure you have them all. I'm going to have 10, and then I'm going to have 2x's, which is the same thing as x squared, 2y's, which is the same thing as y squared. Don't forget the I. And then what I have left on the inside is just this lonesome little x that didn't end up having a pair. Right. I'm hoping we're starting to kind of feel better about simplifying square roots. We've done a lot of it, but now we've introduced, since last lesson, imaginary numbers. With that being said, here's your assignment for today. It's giving you a little bit of everything. Variables, adding and subtracting, multiplying, more adding and subtracting, and dividing. Okay, please make sure, like it says here, simplify the given radical by hand to the lowest terms. Leave in a plus bi standard form. Okay, in other words, in that complex form that we talked about before, if necessary. Okay, guys, if you have any questions, let me know. Other than that, have a great day.